class, this is week 3 summary, and if you remember, we started this session by investigating thermal resistance. And what was thermal resistance about? We basically said we are going to use electrical resistance concept, which says difference in voltage going to create current, and the resistance, the electrical resistance, is going to be RE there. So we generate a similar arrangement for temperature. The motivating or the driving force is temperature difference, and the flow or current we have is heat transfer rate, and whatever left is going to be our resistance, but it's going to be thermal resistance. So for flat wall, we introduce thermal resistance as when we write Q dot equal delta T divided by R. So for the flat wall, it is going to be thickness L divided by Ka, and the unit is degree divided by watt. For convective heat transfer, it is 1 over HA. Of course, area, you know, it's a surface area, the area in contact with the fluid, and you can continue this resistance calculation for radiation. Then we introduced another concept which was very important for us, and it was contact resistance. Basically, the quality of the contact between two surfaces, you can see here, and if it's not perfect, we are going to have some type of temperature drop there. And we calculate a resistance because of the contact, or thermal resistance because of the contact between two surfaces. And as you can see, the unit is a bit different. It is multiplied by the surface area, because the surface area also is a very important factor for the contact thermal resistance. And this is another resistance for us. So then we investigated different cases we can have for the resistances. For example, here we have convective resistance, conduction resistance, convective resistance, and they are in series. So when you draw their thermal resistance network, you're going to draw them as a series, and when they are series, you just need to add to each other those resistance. And remember, it's very important when you write the formula for heat transfer rate Q dot between TA and TB, resistance is going to be between TA and TB. This is very important point. Okay, how about another case when they are parallel? If they are parallel, you're going to add the resistance as parallel condition. So the total resistance is going to be 1 over the first one, 1 over the second one, and so on. How about cylindrical shape? When it's cylindrical, the resistance is going to be this formula. Remember, we extracted previous session the temperature profile formula for cylinder, and we had that ln. So when you convert that formula to this form, this R is going to be this formula, ln R2 over R1 divided by 2 pi Lk. How about sphere? For the sphere is another formula. So be careful when you have a question. If they are cylindrical shape or sphere shape, you need to use the specific resistance, thermal resistance for those cases. Then we investigated extended surfaces or fins. And if you remember, the first assumption we had was steady state. The second assumption was 1D heat transfer. And we considered we are going to have heat transfer in X direction only, not in Y direction. So Y is going to be this direction, not vertically. When we have very conductive material and the thickness of the fin is very small. So we write the temperature balance or heat transfer balance, and then we reach to this formula. To simplify this formula, we introduced theta, which was T minus infinity, and M. So this formula converted to a little bit easier form, and we solved it, and we needed to solve this differential equation. Because it's second order, you need to have two boundary conditions. One of them is here, temperature at the base. Sometimes we write it as TB, temperature at the base. This is given. We need another one. The second boundary condition, we can have 4 different assumptions. First one, let's assume the temperature of the fin tip is T infinity. To have T infinity, or the medium temperature at the tip, it means we need to have very long fin. If you use this boundary condition, the formula you're going to get for temperature profile is going to be this one, and heat transfer rate this one. If you assume you have a fin tip, adiabatic fin tip, the formula is going to be this one, and Q dot is going to be this, and the third one is the case we know what is the fin tip temperature. So a little bit more complicated formulas for temperature profile and the heat transfer rate. And the most complicated one is the case we're considering convective heat transfer boundary at the fin tip. So this is going to be most complicated formula. And as you can see, number 4 is a little bit difficult to use. So we prefer to use number 2, which is adiabatic fin tip. But to reduce inaccuracy, we introduced this concept, which is corrected lengths. Basically, we say we have some type of convection at the fin tip. So to compensate that fin tip convection, we are going to add this amount to the length of the fin, which we are going to have a conduction here, and consider insulated at the tip. So this conduction, because of the extra fin tip, is going to compensate for that convection at the fin tip. And if it's rectangular, you basically add half of the thickness. If it's cylindrical, you add divided by 4, or you just use this formula. This is easier. Cross-section area divided by perimeter. Okay, then I introduced fin efficiency. Basically, it's a ratio of the actual fin heat transfer rate to the perfect or ideal heat transfer rate in our fin. So the ideal fin is going to be the temperature everywhere on the fin is exactly as the fin base. So we can extract the formula for that. Let's go with the next one. The next one we introduced was fin effectiveness. Basically, the ratio of heat transfer rate when we have a fin and when we don't have a fin. Then we talked about what happens if we had fin array, several fins, which usually we have this condition. So you need to add unfinned area heat transfer rate and finned area heat transfer rate. So this is very important when you're calculating heat transfer rate for the fins. You need to consider the fin efficiency, which we already defined. For the unfinned area, the efficiency is 100 because the temperature is exactly the base temperature. Then we investigated what happens if you increase the fin length. So we divided actual heat transfer rate for fin by the heat transfer rate when we have very long fin. If you divide those, we are going to have tangent hyperbolic ML. By increasing ML, basically by increasing ML, which means by increasing the length of the heat sink fin, we are going to have a larger tangent hyperbolic, this value or the ratio. So we want to increase this ratio. So by increasing ML, this is going to increase. But you should know the rate of increase is going to decrease as you're going further. So if you consider ML5, it's going to be 100%. So we know we're never going to select 5 because we don't want to have really, really long fin because the efficiency of the material used will be very low. So you may need to make a decision. Do you want to stop at 98%? Do you want to stop at 90%? It's your engineering decision. So at the beginning, when you increase lengths, you can see we have high change of heat transfer rate. We call it high heat transfer area. Do you want to stop here? Or do you want to go low heat transfer area? Stop here, your fin length. Or we don't go this way, no heat transfer area, it's just waste of the material. So another point we investigated was when we have several fins in our heat sink, we can do the calculation and convert the formula to this form, which we can introduce overall efficiency of a heat sink, which is the formula, and it includes the efficiency of the one fin. Because we converted everything to the form we are familiar, which has H, total surface area, and delta T. Whatever is left should be efficiency, and we called it overall efficiency of heat sink. This is another point. It's about conduction shape factor. Basically, for complicated geometries, if we have frequent use of those geometries, some scientists extracted the formula for those cases, and they introduced the formula in this form. So, as you can see, we have temperature difference here, thermal conductivity, times a constant number. That constant number depends on the area, geometry, what is happening with that geometry. And we have some tables to show us what is this S. For different geometries, people extract this S, and we call it conduction shape factor. And for example, one of them is if we had a pipe under soil, what is going to be heat transfer from the pipe to the surrounding? So you want to calculate that heat transfer. So it's complex geometry. We don't have a specific calculation for that. So that is why we have a table to show what is the S, this constant formula for this geometry. You put it here. You know the conductivity. You know temperature difference. You can calculate. So this is like a specific case for a specific geometries, which we have many applications for that. So some researchers extracted this conduction shape factor. That's it. See you next week.